Hey class, so for today's video, I'm going to be going over the code for LU decomposition. So the first thing with LU decomposition is to remember the equation and what actually you're doing. So you need to remember that the first step in LU decomposition is you're splitting the A matrix or the coefficient matrix into upper and lower triangular matrices. And so it's always good to remember this equation here, because this essentially gives you the steps for LU decomposition. The first step being decompose A into upper and lower triangular matrices. Then you solve the system of equations L D equals B, and that gives you the D vector, and then you solve UX equals D to get X. So by solving L D equals B, you're using forward substitution, and then UX minus D, you're solving with back substitution. So let's go ahead and get into the code. Let's use the matrix that we have been using for the other methods of solving systems of equations. Okay, so now we can define our rows as the length of A, or you can use any other built-in function to get the rows. So we're initially going to define our lower triangular matrix as the identity matrix of R, of rows and columns. The identity matrix is size R. This is our identity matrix. And this is our lower triangular matrix placeholder. Okay, and so now we can say U equals A. And so let's go ahead and do the elimination step, which is A equals L times U. Okay, and if you guys remember, what we're storing in the lower triangular matrix is the factors from the elimination step in Gauss elimination. So you can go ahead and iterate from for I equals 1 to rows, and then for J equals I plus 1 to rows. So this will be our incrementing column for loop. Increment columns, and this increments rows. And so now we can go ahead and call our factor U of row J, column I, divided by the main diagonal. And then so we'll say upper triangular matrix of row J, we're going to do the row operation. Okay, and then go ahead and store in the lower triangular matrix in row J, column I equals a factor, and then end, and then end. And so we can go ahead and see what that looks like. So save this code, LU decomposition. And then you'll be able to see this lower triangular matrix with the factors stored, and then you have the upper triangular matrix. And so in this elimination step, you can also use pivoting, but you need to be careful when you're using pivoting with LU decomposition, because when you go into into the forward substitution step, you're going to have to remember, the algorithm needs to remember what you pivoted. And so that's why I don't recommend initially implementing pivoting in your elimination step to understand LU decomposition. But then when you get more comfortable, then you can implement it. And the book has a good section on it in which that describes using the permutation matrix to keep track of these row operations. That way, when you go and solve with forward substitution, you will be able to get the correct answer. And so let's do the forward substitution step, which is L D equals B. Okay, and so we'll go ahead and define D as zeros, a column vector, and we'll say D1 equals B1, and that's just from the nature of the lower triangular matrix. As you see, if we have LD equals B, then when you multiply D1 by the coefficient matrix, it equals B1. And so just like with back substitution, you need to define that first element, or in back substitution, the last element. And that's the only hard coding you need to do. Now we can make it now we can make it general. So for this will be from 2 to the row D of I equals B of I minus the lower triangular matrix of this is I equals I all times D. So this is the dot product. So this is row I. So let's say this next row, you have D here, okay, and then you have B here. Let's just say, for instance, so you're going to multiply dot product D times this, and then what you're doing is you're subtracting over. So this is going to be 0 right now. You subtract this over, and then you say that D of I equals that. That's the dot product operation makes this 0, and so you're only subtracting over this. And then the next dot product operation, once you solve those two, this becomes 0, and then you're subtracting these two over, and then this is what you're solving for. Okay, so now we have the D matrix, or the D vector. So now we can do back substitution of U X equals D. Okay, and let's look at what the U matrix looks like. So as we know with back substitution, you need to define first your B matrix. Okay, or we'll call it X, your X matrix. Okay, now we need to define the last element in back substitution, and it's just like with forward substitution. This is the only thing that you're going to hard code, and the reason why is because this last element is hard. I don't think you can make this completely general. So then we have X of n equals our D of n, because this is equal to D, divided by X, or U of n row, the last row, and then last column in U. Okay, now we need to write our code. So it's for I equals row minus 1, so -1 to 1, and we'll say X of I equals, go ahead and put parentheses, D of I. So this is equal to D. then this is a row, the current row that we're solving for in the first iteration will be this one. So what we want to do is subtract the elements that we've already solved for. So this will be u of I, row I, to the end, or actually all, and then we're taking the dot product of x. And so currently x only has one element solved for. That's not 0. So this is the element that's going to be subtracted, or in this case added because it's negative. And then we have to divide by the main diagonal, because this is what we're dividing by. And now you have solved iteratively for x. And now we can display x. And then let's go ahead and put, for speed purposes, tick tock. And so in the next video that I'll post, I'll demonstrate the speed difference between LU decomposition and Gauss elimination. But let's go ahead and run this, and we can compare it. So we'll say a aug equals a b, and then we can do ref, or we can do, actually we can just do \b. And is this the same? Yes, it is. And so you have solved the system of equations without using Gauss elimination, using LU decomposition. So I hope this helps. See you in the next video.